Thanks very much, Chris. It's a real pleasure to be here today to talk to you guys. Are you having fun?
Yeah.
Has it been a fun week? Yeah. I hope it's just getting started. I want to tell you that as a scientist, as somebody who spends their days thinking about ideas, it is the most fun thing that I know. People say to me, why don't you go on holidays and lie on a beach and do nothing for a while? Because I get bored. And I think I'm like many of you. Ideas and thinking about ideas are fun, and it's what gives us tremendous pleasure in life. So let me encourage you, as many others have done this week, to think about your futures and think about your careers in science and in ideas and in using your brains and imaginations. I'm going to give a talk today on, as Chris mentioned, this field of quantum nanoscience. I'm going to tell you exactly what that is. I'm going to give you my opinion, so you can water it down with your own or mix it up with somebody else's. That's totally fine. Realize it's my opinion. But before I get started, let me make a point that I really want to sort of get across to you guys. I'm going to be talking about some hard science, things that are going to take an awful lot of time, an awful lot of money, and an awful lot of patience. And I wanted to, first of all, acknowledge Harry's incredible vision. This science school has been in action for twice as long as I've been alive. And these are the type of timescales that people have to think about to really do something in science, to do something that matters, to have a vision and to have that vision stretch out over the decades, blown about day by day, week by week, year by year. Things come and go. But the sustained vision and idea and strategy to actually make a difference to young people like yourself is something that is truly remarkable. And it's really quite an honor to be here and talk to you today. Let's talk about nanoscience. There was a great question on Monday after the first speaker, Michael Ruckus's talk. Somebody asked the question, what is it about the nanoscale that's important? Could we go beyond that? Maybe we could make technology from quarks or maybe something even smaller than that. Who was it that asked that question? It was one of you guys. Probably too embarrassed now to put your hand up. But it's a great question to ask, and it had me thinking. And, Michael gave you a particular answer. I want to maybe try my hand at a slightly different perspective. Let's ask the question, is the nanoscale somehow special? Why aren't we talking about centimeter science, millimeter science, kilometer science? Is there something about the nanoscale? And I hope to bring across in this lecture that there certainly is. And what I think is one of the key aspects of the nano realm is that it's this bizarre properties of quantum physics that want to live in the nanoscale. It's their home. And I want to show you that is very powerful for some of the technological things we want to do in the future. So why is it that nanoscience or the nanoscale, why is it so rich? Why is it so special? Well, it's a hard question, but if you really start to think about the building blocks of matter and physics, what are the length scales? What are the forces? What are the length scales of electromagnetism? What are the length scales of quantum interactions? Okay, the nanoscale is not the natural scale of gravity. Maybe that's this type of scale. Gravity has a natural length scale where you really see some complex behavior, some spectacular shapes and dynamics of galaxies play out on very large length scales because the gravitational force is so weak. At the nanoscale, though, things are different. I want to say that the nanoscale is the natural home of those types of forces, of quantum interactions, of bonding, of van der Waals forces, all of these types of things that build up a very complex picture of matter. But maybe you disagree with me. I want to show you something that you might like, and I certainly recommend you play with it. Many of you guys have seen this. So if you haven't, take down that URL at the top there. It's the scale of the universe, and it's a fantastic online resource. So here's the scale that we're at, human beings, and, okay, some weird-looking giant crab-like creature that I hope is not on our scale. But what happens if we shrink down? Okay, so what I want you to think about is look at the complex structure that you see. These are pretty complex things. There's a lot of things here. Even down at this scale of microns, there's still a lot of things, a lot of different types of things. But as we start to really get into the nanoscale, and then there's a nanometer, and now we're going to push beyond, okay, there is things down there, but look how much white and grey space there is. I don't see many coloured blobs of interesting things. I see that we're going down by orders of magnitude further and further and further, and there's just not much there. So, okay, build a technology or a science at that scale. Your toolbox is the top quark. Well, okay, I'm not saying that in some decade, sometime soon, we may not, well, who knows? It's hard to predict the future. It may be possible to create technology based on quarks. But naively looking at what we call degrees of freedom, the availability for interactions and for putting things together in different combinations. The nanoscale, as you start to scale up, by the way, we haven't even gone anywhere near the bottom there. Look, we've got lots of, and then we end up with like a red bar. Okay, but if we come back up to the nanoscale, what happens at the nanoscale, look, things start appearing like crazy because we've switched on a size scale where the forces and the interactions start to be complex enough that you can really build things that are complex. Okay, so it's to me, a statement about complexity. And as we scale up further, that complexity is layered on that microscopic, that nanoscopic level. And of course, we end up with things that we know. We can go to the other extreme as well. Planets, galaxies, stars, whatever else. And there are different interactions. Gravity is really holding sway there. Okay, so check that thing out. Let me go back to the talk. All right. So hopefully I've convinced you that the nanoscale, the nano realm, at least, has the ingredients and the complexity needed to create very interesting things. So let's look at life as an example. Life is perhaps one of the most unexpected and complex things we know. Imagine if you'd never seen life before and, I don't know, you looked at a planet and I gave you the original laws of physics and said, here, figure out whether life would spontaneously create itself or not from the basic laws of physics. That's a very hard question. It's a very hard problem. And yet it does, and yet we have such things as leaves and trees and plants and people, very complex entities that almost self-assemble themselves from these basic ingredients. But although the nanoscale is this realm of atoms and molecules where quantum physics is at play, I want to tell you a dirty secret, and that is we don't know why quantum mechanics really disappears as you start to scale up. We have some hunches about that. I'm going to suggest that, in fact, it's an engineering challenge to take the weird behavior that I'll start to talk about in a moment, quantum physics, quantum behavior, and extend it, allow it to exist on other length scales beyond the nano realm. That's a fantastic scientific and even engineering challenge as to how to make that happen. And I think it's one that's going to occupy some great minds over the coming decades. So keep that question in mind. Where does quantum physics turn on? Where does it turn off? Where does classical physics turn on? Where does it turn off? What's that boundary between quantum and classical? And how can we push that boundary further and further, higher and higher in scale, longer and longer times? That type of work is already underway, and just a few years back, a group at University of California, Santa Barbara demonstrated that you can take an object that's nothing more than a tuning fork, you flick it and it wobbles and rings, and you can have that oscillation, that motion of that cantilever, that tuning fork, be in a superposition of states. It can be cooled also to the ground state, what we call the ground state. It's quantum mechanical, fundamental, zeroth energy level. What's interesting about this particular experiment is that you can see that object with your eye. So if you go back in history and you ask the question of, I don't know, whoever your favorite scientist back in the day was, Einstein or Bohr or something, and say, can you imagine seeing something with your naked eye that also exhibits weird, strange quantum mechanics? That type of behavior? I think they would say, don't think so. With a very different accent to me. Okay, so this boundary between quantum and classical, it's not a hard boundary. There are examples where you can push beyond. We don't really know yet how to extend that right up to the level where humans exist, but we really don't even understand the basics of what defines each one of these realms. So I've told you that quantum physics is living in the nanoscale. Let's talk a little bit about what quantum physics is. I know that many of you have quite a detailed understanding of what quantum physics is, but maybe some of you don't. So let's take a little bit of a step back and talk in very general terms. I'm not going to condense an honors course in quantum mechanics into 30 seconds, but let's talk about some of the key points of quantum physics, because that's going to be very important for some of the things I want to talk about in a moment. Around about 100 years ago or so, it was noticed that light, electromagnetism, which was understood at the time to be made up of waves. What's waving here is the electric field, the magnetic field. It was understood at the time that, in fact, light sometimes behaves not as a wave, but as a particle, as a ball, as a, not a tennis ball, but as a tiny packet of energy that, for all intensive purposes, looks like a localized thing, a particle. So many of you would have heard of this wave-particle duality. And, okay, that's pretty wacky to begin with, to think of light as both a wave and a particle, and you'll hurt your head if you do that long enough. Maybe something to do when you can't get to sleep. But the really strange thing is that matter, which we're very familiar with, we have intuition about what matter is from our everyday experience, but yet matter can also behave like a wave. How many of you have seen matter behaving like a wave? Well, I'm not talking about waves at the beach or anything like that, but actually, in a quantum mechanical sense, matter can behave like a wave. And I hope that many of you are starting to think, I'm not really following. I kind of hear the words and stuff, but I don't really know what matter like a wave is. Good, you're in good company. Nobody really knows what that means. And the key question is, well, what's waving? Do you mean like matter that's just kind of doing this? Like, so if I sort of squashed it and stretched it, no. Where it gets hard to imagine and think about is when you realize the thing that's doing the waving is something very, very strange. It's something called the wave function. Well, not surprising. But the wave function tells us everything that we could possibly know about a quantum system. For instance, the wave function tells us about the location, the position of electrons in a hydrogen atom. Okay, so as you change the atomic orbitals of the hydrogen atom, what's shown here in the color scale is the probability of finding the electron at a particular location. We get that probability from just squaring the wave function. So what's waving now is the probability of finding an electron at a particular point. That's the thing that has all of this funny shapes and dependencies. Okay, it's not just position. You could do a measurement of the momentum of an electron. That would also be described by the wave function. Very strange concept, and yet it works extremely well, and it underpins all of our technological life that we have today. It underpins the operation of transistors, lasers, even really basic things, not technological things, how we understand light scattered off glass or anything else. An extremely successful theory, in some ways our most powerful theory, but also our most bizarre theory in a lot of ways. I'm going to tell you about some of those bizarre properties and how we think we can use them for technological means. So let's talk a little bit more about this wave function. Many of you have done waves in physics, and you know that what matters when you add up waves, we call it superposition. You know what matters is the phase. If two waves come together and they're in phase, and I have superposition, then I get a wave that is twice as big, right? But if the phase is out by 180 degrees, if there's a peak and there's a trough and they come together at the same point in time and in space, they cancel one another out. The same is true for probabilities. The same is true for the wave function that describes quantum mechanical entities. Phase of that wave function matters. So we can have a situation where interference, that is one wave overlapping with another wave, leads to peaks and troughs or bright spots and dark spots in the optical interference pattern of light. And the same has been seen and observed for electrons, even atoms, even larger scale objects, molecules. What do you mean molecules? I'm talking about molecules that interfere with each other in terms of their wave function and cancel one another out so that the probability of finding a molecule here is 0 and finding it over here is very large. So that's some pretty strange stuff. It's going to get a little stranger. The act of measurement in quantum mechanical systems is something really counterintuitive. And I have to say that I'm familiar with the language, and I've been doing this kind of physics for a number of years, and so it's very easy to just adopt a framework by which we think about these types of problems. But if I put that to one side and really try and understand what's going on, I get a headache. You should be getting a headache. If you are, you're probably starting to grapple with some of these concepts. Let me tell you what I mean by quantum measurement. Here's a piece of glass. It's a window frame, window pane. Out of that laser, it doesn't have to be a laser, it could be any light, it could be the light in your bedroom, is coming a stream of photons. You know that some are reflected, not many. If it's regular glass, maybe it's about 4% get reflected. Most of them are transmitted if it's half-decent glass. 96% transmitted, 4% reflected. Okay, let's dial down the strength of that light so that one photon is coming every now and then. And now I'm going to say to you, I'll give you, I don't know, $1 million if you can tell me whether that particular photon that's coming right now will be reflected or will it be transmitted through the glass? We'll do both. Well, okay, might do both. Can you say whether it's going to be reflected? Can you say whether it's going to be transmitted? All you can say is, I can say it's 4% chance of being reflected, 96% chance of being transmitted. You can just give me a statistical answer, probabilistic answer as to what that single photon is going to do. Now, how many of you are thinking, you're hiding something here? You know, if I toss a coin, the only reason I can't tell you it's going to be heads or tails is because I can't calculate every possible detail of how the coin spins and the viscosity of the air and the interaction with the molecules. And if I had a supercomputer and I could do all of that, I'd tell you whether it'd be heads or tails because I'd just model it. That may be true for a coin. As far as we know, it's not possible at the quantum mechanical level. The theory itself, the reality of nature itself, is statistical, is stochastic, is probabilistic. Okay, there's no microscopic theory underneath all of that that we just don't know yet, and if we did know it, then we'd be able to predict exactly. No, we believe that that's not the case. That seems like a very arrogant thing to say. We don't think that there's a microscopic theory underneath. The reason I say it is because experiments we can do to try and see whether there's something deeper under there tell us that there isn't. Tell us at least that this description of nature in terms of statistics is the correct one. Now, that doesn't mean it's not powerful. It doesn't mean that it's not fundamental. It's just that the foundational theory is one of statistics. We don't know how to interpret that. Many of you have probably read books about the interpretation of quantum mechanics. And boy, there's some pretty wacky ideas there. You can decide that every time a photon's reflected or transmitted, the entire universe splits in two. One's transmitted and one universe where it was reflected continues on. Are people just taking some pretty good drugs or something? Or, where do they get these ideas from? LSD? That's an interesting side story I'll tell you about in a minute. But the reason is because we don't know how to fit quantum mechanics into our intuitive understanding as human beings. Our brains are wired a certain way, and trying to make sense of this stuff in the language that we understand is very, very hard. Okay, we have to follow the mathematics and see where the mathematics leads us. Okay. This is a pretty misunderstood experiment. If you haven't heard of Schrödinger's cat before, let me very quickly say what that is. It's a thought experiment. A thought experiment was the way you do thinking back 100 years ago or so with a coffee in your hand in a nice European cafe, and you propose an experiment, knowing full well we're not going to do the experiment, but imagine what would happen. So a thought experiment that was proposed, what I showed you here, is to say, okay, quantum mechanical objects like electrons and photons and the like, they can be in a superposition of states. They can be both here and there, or they can be polarization vertical, polarization horizontal, spin up, spin down. They can be in some superposition of both. Why don't we wire up some kind of clever apparatus so that whether an electron is on the left or the right triggers the release of a poisonous gas? Let's put the cat in the box, and if the electron is in a superposition of states, the cat's going to be in a superposition of states, dead or alive. Until we open the box and look in there, at that point we do something called a quantum measurement, and we use the language of saying we project the state. It's no longer in a superposition. We project it into one of its two outcomes. The dilemma here, or the thing that was in Schrodinger's mind when he was proposing this idea was, how do we incorporate that microscopic quantum mechanical behavior of superposition? What are the consequences when we couple it to macroscopic objects? So what does happen? What do you think? What's the answer to this question? Anyone know? Both. So you think that if we do this tonight, late, after a few beers, we're going to get a cat in a superposition of dead or alive? The cool experiment would be to do it to you, because then after the event you can tell us, assuming you're alive, what it was like to be in a superposition of dead or alive. Okay. The trick is, if you want to have a superposition state, you can't make a measurement. The environment can make a measurement. If you really want to have a superposition of dead or alive cat, you have to seal that box so perfectly that there is no interaction at all with the outside world. Because if there's an interaction with the outside world, what's going to happen is something called decoherence. So there's a few basic principles here that I'm trying to bring across. We've got superposition, but then when we make a measurement, we have an outcome. If there's an electron in a superposition of left or right, and then you do a measurement, it's either in the left or it's in the right. It's like the photon that's either transmitted or reflected. Okay, you don't do a measurement where you're like, well, it's kind of transmitted and reflected. It's pretty... No, it's either one or the other after the measurement. But the environment, the surrounding thing, can also do a measurement. We use some funny language to describe that. We can talk about what I'll say in a moment, entanglement, and how the environment gets mixed up with the object so that the two are no longer separate. But the important thing that I want you to realize at this point is that quantum systems are extremely fragile. If you open the box and look at the cat, it will be in one of two states. You would have collapsed this superposition state. Quantum systems are very fragile. Okay, so let's use that fragility to do something useful. What can you do with a very sensitive system? How sensitive? Well, quantum mechanically sensitive. What does that mean? It means the types of issues we're talking about. If I observe it, or if the environment changes and observes it effectively, then I can detect some outcome. Recently, colleagues of mine at Harvard University have used the properties of single nitrogen atoms in a diamond system. They made a chip here with diamonds, and then in those diamonds they put nitrogen atoms, and it turns out the property of that nitrogen atom in diamond creates a very, very sensitive quantum mechanical system. If you interrogate it, it can tell you about its environment. Basically, you put it in a superposition state, and then after some time, the environment projects that superposition into one state or the other. And you can then observe that projection. So this is very interesting. We're using that sensitivity, the fragility of quantum systems now as a probe of the environment to image on the nanoscale biological systems. Okay, can't you do that with an electron microscope? Of course you can. Try doing this with an electron microscope. I want to map out the magnetic field profile of nanoscale, biological systems? What about the organelles inside a earthworm's cell or something? What's their magnetic field? What's their electric field? So the first point I want to make is that quantum physics in the short term, over the next few decades, is really going to be exploited by making use of this really fragile aspect, the sensitivity of quantum systems to decohere, to project into one state or the other. Turning that around and saying, yeah, how do we use that sensitivity as a means of detecting and sensing things on the nanoscale? Let's get on to some of the more wacky properties of quantum physics. I need at least 30 to 40 one-hour lectures to really get to the bottom of what's going on here, at least to get to the bottom of what the question is. And I'll leave you guys to try and come up with the answers over your lifetimes. Quantum entanglement is something very different to quantum superposition in the sense that superposition, we're kind of familiar with it. If you go to the beach and you watch waves collide, you sort of understand superposition. I cannot give you any analogy of quantum entanglement. I can't say, oh, it's kind of like, it's not. I'll try and come up with one, but it doesn't really do it justice. What is it? To me, it's the most bizarre thing there is. I know some pretty wacky people, but this is the most bizarre thing I've ever seen. A source of particles, let's assume they're photons. They could be electrons, they could be anything you like. I'm going to say they're entangled. We'll see what that means. So they come out of a source together, and they're entangled. If they're photons, let's say that their polarization, whether the electric field is moving this way or whether it's moving that way, so oscillating in the vertical or the horizontal, I'm going to say that the photon on the left is vertically polarized and the photon on the right is horizontally polarized. And they came from a source of entangled photons so that it spits out pairs of these guys such that they're always anti-correlated with one another. Now, if the one on the left is vertical, then the one on the right is horizontal. If the one on the right is horizontal, the one on the left is vertical. I can understand that. Let me take your mind back, though, a few slides ago. Do you remember the question about, tell me whether that photon's going to be reflected off that glass or not? You said, well, 4%, 96%. Yeah, but tell me whether that one's going to be reflected. Well, I can't. So quantum measurement is statistical. So here comes our photon. Do a measurement and tell me whether it's going to be horizontal or vertically polarized. Or I can only tell you it's going to be 50% one way or 50% the other way. I can't tell you for that one photon which one it will be. Same on this side. Okay, so do a bunch of measurements. Do 100 measurements. So it's horizontal, horizontal, vertical, horizontal, vertical. On this guy, do the same. 100 measurements. You'll see 50% of the time it's horizontal, 50% of the time it's vertical. Now take these two data sets, these measurements and these measurements, hold them up side by side, and you're going to see that every time that one was horizontal, the other one was vertical, and vice versa. What's bizarre is, how did that one know that it needed to be horizontal when that one was vertical? Because we already said that you can't predict the outcome of the measurement. Whose brain's hurting? Yeah, me too. That's some really strange things. It says that these guys share some information non-locally across vast distances. Take them to the other side of the universe. Make a measurement on this one. This guy's always the opposite. That seems like a pretty cool thing. Why don't we have that in our iPhone? That's a cool resource. Everyone know what a voodoo doll is? Yeah. It's kind of like voodoo. You know, you want to hurt somebody, so you stick a pin in the doll, and then, oh, they're, on the other side of the city, and they get a pain in their eye. All right, the reason it's not like voodoo is because of that quantum measurement aspect. It's not just that the other thing does the opposite, even though it's separated by a huge distance. It's not just that it feels the effect. It's also that before we did the pin in the eye, the outcome wasn't known. and yet the particles still correlate with each other. You know, in the 70s, people got interested in this for a whole bunch of really wacky reasons. The first thing was they thought, okay, maybe quantum entanglement explains telepathy. Maybe people's abilities to, you know, be able to think about what's coming in the future or be able to read your mind and these types of things has something to do with quantum entanglement. If my brain and your brain shared some entangled particles and I do a measurement by thinking we're linked somehow, okay, well, you might guess that that turned out to be not quite true. But it's a very interesting and real science story about those types of ideas back in the 70s and early 80s, because in refuting those scientific ideas, we actually developed a very deep understanding of quantum information and quantum entanglement and what it can do and what it can't do. If you're interested in this stuff, you should read this book. Another suggestion was maybe this allows us to transmit information faster than the speed of light. If I have these two particles and they're entangled and I do measurements on this guy, then don't I kind of learn about the other one? Haven't I transmitted information across a vast distance? It turns out that no, that doesn't work. What a shame. You do all the measurements on this one, you do all the measurements on this one. Unless you compare them, they just look like random noise and random noise. It's only when you bring them together and notice that they're correlated. So it doesn't allow you to transmit information faster than the speed of light, but it does allow for a sharing of quantum information non-locally across different systems. How many of you have seen this movie? Anyone? Okay, don't see that movie. It's really bad. But it does point out how once you start to talk about things that we really don't understand, a lot of people like to hook a ride on that and use it as a vehicle to make up all kinds of stuff. Interesting. Okay, let's sort of shift gears a little bit. I've told you about what quantum physics is in some sense. I want to say a few words, and I wanted to say them right, so I wrote them down on the screen so I could read them. Okay, so the first is the decoherence, that collapsing of the wave function into one of these states. The measurement of the system, whether we measure it or the environment measurement. Decoherence robs us of quantum behavior like superposition and entanglement. If the environment does a measurement, then the cat is in one of two states. It's really in one of those states. It's no longer in a superposition. I want to pose the question, what if we could suppress this decoherence? What if we could keep that cat in a state of superposition? So quantum systems alive. We don't know what consequences that would lead to. If we could control quantum systems at the level that we could prolong their quantumness, we don't know what technological powers we would have. This has got to be something really exciting if you take this thing in red seriously, because I believe it to be true. In your lifetime, we're going to get pretty far towards an answer, I believe, to this question. We may not realize all of those technologies, but I think over your lifetime, we will develop a detailed understanding of what is possible based on these wacky and strange properties of quantum physics. Okay, let me shift gears a little bit. I want to tell you about some of those bizarre things and some of the technological power that we imagine are waiting for us if we can harness, in some sense, these quantum mechanical properties. The first is computing, information processing. So I'm going to end up talking about quantum computing. I know many of you have heard of that and know something about that. To give you a background, I want to really take a bit of a step back and try and understand what computing is, because we're not really going to understand what quantum computing is or why it's powerful or why it's interesting and why so much money and effort's going into it if we don't really understand, well, what is computing and what is its limitations. There's a few people in the front row that had a significant hand in the development of various things that you see on the view graph here, from transistors to this system over here that was actually in the School of Physics some years ago. The history of computing is one that is very rich and filled with not just engineering, but also very deep physics. That it's even possible at all to process information using mechanical devices, electrical devices, or switches, transistors, is kind of weird. We take it for granted. But I find this very strange. I mean, it's some property of mathematics and it's some property of the world we live in, of nature, that you can process information, you can do calculations, you can do many, many things that lead up to you being able to check your status on Facebook because a bunch of switches are wired in a certain combination. And we've got switches that switch switches. And those switches switch more switches. And then there's some feedback that switches the original switch a different way. Okay. Logic gates, very, very basic ways of processing switches being on or off. If you concatenate these things into various combinations, it's remarkable, but it's true, you can process information. Let me encourage those of you that have not really heard of this to dig a little bit deeper and try and understand what's in your laptop. How is it that it's just light switches, effectively, wired together? Amazing. To do powerful things, you need a lot of switches. Since the beginning of computing, beginning of transistors, and the start of integrated circuits, a lot of the power of computing has come from being able to cram more and more switches, more and more transistors onto an integrated circuit. Now, this is a nanoscience school. We're talking about nanoscience. I'm now deep into some sidetrack on computing. The reason I can get away with that is because I want to tell you about the size of these things, and I'm going to make the bold claim that you already have nanotechnology in your pocket, in every sense. Look at the feature size of transistors, the size of transistors as a function of the years that have gone by. What's remarkable is where it even starts. Look at this. Mid-70s, we've got transistor feature sizes of a few microns. So that square there, that's a human hair, and that little box there is 10 microns. That's up here. So already in the mid-70s, we're kind of smaller than that. And over the last few decades, incredible efforts have led to a scaling of transistors smaller and smaller and smaller. Why do you want to make them so small? Well, because we want to pack so many of them onto an integrated circuit. Well, why don't you just make the integrated circuit bigger? It's a really good question that people don't actually ask. The reason is, when you do that, information's got to propagate from one side to the other. And the fan-out problem is an engineering challenge, but there's some really physics reasons why when you make it bigger and bigger, it gets harder. Imagine that the signals were propagating at the speed of light. Okay, if I make a massive thing where information's got to go from one side to the other, it takes something like 20 nanoseconds to move a meter. So that's going to limit the speed of operation, and it's going to lead to a pretty challenging problem of how to synchronize and coordinate these systems if they're large. No, what we want to do is keep the size of the thing the same, so we don't have to worry about propagation. We just need to make them small so that they can all talk to one another. Here's some real nanotechnology. This is just incredible. This is Intel's latest architecture, Ivy Bridge. That's 1.4 billion transistors on a chip. It's a 22 nanometer feature size with a 4 gigahertz clock. You can make them on a giant wafer, and you can pump them out at a huge rate and put them in the pockets of large numbers of people. That's really phenomenal that that's possible today. Look at that thing. By the way, if you're interested in that, you can find web pages that let you zoom up on certain regions, and you can really study the incredible engineering and creativity that's gone into creating such a thing. It's the evolution of a long investment over many, many years, and it's still going. That's nanotechnology. Okay, let me tell you something else that I've really been thinking a lot about recently, and this is, I want to try it out a little bit on you guys, to be honest. Often we talk about hardware, and we talk about the scale of transistors and the incredible power that comes when you have this type of hardware. But hardware needs software, and it's also amazing the power of software. What happens when you type cats with mustaches into Google. You press enter and what happens? Pictures of cats with mustaches appear. You can do it with anything you like. And in a split second, you get as many images as your brain can deal with, whatever it is you search for. That's amazing. And it's not just the hardware. It's not just the number of transistors and their scale. It also has everything to do with the creation of efficient algorithms. Okay, so what's an algorithm? An algorithm is an instruction, a series of instructions of how to do something. The trick is efficient algorithms. Imagine, you get a jar of jelly beans. And you get to guess how many jelly beans. How many of you look at the thing and go, it's about 10 centimeters by about 25, and try and estimate the volume. Then you estimate the volume of a jelly bean, you kind of get roughly there. Some of you do that? Yeah. That's a very, very basic algorithm. It's a lot more efficient than counting them out one by one. Okay, so it's a trivial example. But my point is, you can calculate things different ways. You can count them one by one, or you can kind of use some formula. Google search actually makes use of some really complicated mathematics. I don't really understand it. There are people around that do. And it's not easy. It's not trivial. It's a hard math problem. If you didn't know that it was related to search engine stuff, and I just showed you some math, you'd be like, it's kind of super abstract, and I don't know where you're going to use that, and surely that has no technological importance. No, it does. Hard, deep mathematical problems have tremendous technological importance. Okay, so I've been thinking about this a little bit, and I'm sort of, to be honest, a little inspired by this idea because I think it has something fundamental to say. I don't know, I chose just almost by accident, I tried to pick 4 pillars of our kind of modern society: information, finance, communications, medicine. And really, I don't have to think too hard about it. You instantly realize there's a clever algorithm that makes it possible. Search in Google is this PageRank algorithm. We're doing tons of transactions every single day in finance. A lot of those transactions are actually built on cryptographic algorithms that were invented in the 1970s that make it possible. Without that algorithm, it doesn't matter how much power you have. Communications, there's people down the front here that know very well about some of these details. The fast Fourier transform is an efficient algorithm that is absolutely key to the operation of your mobile phone, of Wi-Fi, of anything else. Good luck doing CT, CAT scanning, or MRI if you don't have an efficient algorithm for tomographic reconstruction. How do you get an image out of all of the data that comes out in slices? How do you put that back together? It's an efficient algorithm. If you had to do it the hard way, the brute force way of assembling an image by pixel, you'd never get there. So efficient algorithms power our modern world. Some years back, the US government released a very interesting document. I'll tell you the truth, just don't share our secret with anybody else. It was written by scientists. Anyway, they got the language very nice here. And I'm going to read this to you because I have to say I find this language really great. It's inspiring, and to me it captures the key issue of my research. Let me read it. Our society is being transformed by an information technology revolution that began with the first electronic computer in the early years of World War II. At the core of this revolution is the concept of a programmable digital computer, which turned out to be the foundation for what economists call a disruptive technology. Actually, a whole family of technologies. That's certainly true. These technologies all have their limits inherited from the original model. We know today that some important problems are just too hard to solve with any computer based on the original principles. And these limitations are not easy to overcome because they're embedded in the foundations of logic itself. This fact reassures us that some important information applications can be protected by wrapping them with one of the impossible problems. But today we know this reasoning is flawed. So the reasoning is this logic. Another platform exists that has the capabilities beyond conventional logic and therefore not subject to its limitation. That any actual physical system could behave in an illogical way is almost unbelievable, and the early discoverers struggled against ingrained perceptions that were only surmounted by hard data from many experiments. Scientists have been aware for 8 decades that quantum mechanics describes nature in a way that surpasses conventional logic. But we've not yet, until quite recently, the practical applications have become apparent. The odd quantum behavior is prominent at atomic scales but fades away rapidly in large ensembles. What is it saying? It says that all of that logic, all of those switches wired together that gives you Facebook, that model of processing information, of computing things, is limited. It is limited to certain types of problems, and we know that there are some problems that are just too hard to compute using that way of doing things. We also know that quantum mechanics, those bizarre properties of superposition, quantum measurement, entanglement, provide a way forward. Go to Wikipedia and type in quantum algorithm. If anyone tells you that there's only one quantum algorithm or something, they're a little bit behind. We have families of quantum algorithms. What are quantum algorithms? They are algorithms, efficient algorithms. Okay, so tricks to counting the jelly beans, but they require quantum mechanical systems to run. We have to build now quantum hardware. Of course, we're going to discover more quantum algorithms as time goes on. This is just a short list of what Wikipedia can throw up today of what type of quantum algorithms are out there. Most of them look like crazy math problems, triangle finding problem. Look at these things. I mean, not invariance. It sounds like deep math. Hopefully, I showed you with the PageRank algorithm that algorithms that are based in deep math have tremendous practical implications. So here we are today, a little bit different to classical conventional computing. You know, for conventional computing, people certainly had algorithms, but the algorithms sort of developed as the technology and the hardware developed, and I think they inspired one another. We're in a bit of a different situation that we have these algorithms. We know how to do incredible things, solve certain types of problems efficiently. We don't have the hardware, not at all, in which to run these types of quantum algorithms. In the remainder of the talk, I want to try and show you where we are today with building the hardware. And I want to tell you a little bit about my specific efforts at the University of Sydney to start to put in place the building blocks, the logic gates for a quantum hardware. Of course, it's nanoscale. The bit 0 or 1, the switch being on or off, is the classical unit of information. In quantum systems, it's the qubit. And it's very similar. The only difference is that instead of being in 0 or 1, we're going to allow our qubit, our quantum bit, to be in a superposition. It can be both up and down at the same time and anything in between. So we often draw a sphere. We call it the block sphere. It's used to represent the phase information of that unit of quantum information. If you're interested, read more on that. You won't need to know the details in order to understand what I'm going to talk about. How are we going to build quantum hardware? Imagine that as an assignment. Your science teacher says, okay, well, I would like you to build a machine for which I can run a quantum algorithm. How are you going to do that? Well, where would you start? You want a quantum system that can be decoupled from its environment. Remember the cat in the box. I said that if we open the box and look at the cat, the quantumness collapses into dead or alive. We want to keep the cat in a state of dead or alive. We want the cat to be in a superposition. So we can't open the box. We have to decouple quantum systems from their environments. That's really challenging to do. So you might first of all choose some kind of system, some degree of freedom in which you can isolate the quantum system dramatically from its environment. The other thing is we know that, of course, like classical machines, I showed you the latest Intel processor, we're going to need at some point to scale up a very large number of these things. I don't know how to scale up anything unless I print it out with nanolithography. Okay, so the way in which you make an integrated circuit like that Intel chip is using lithography, printing methods effectively, which I'll show you about in a moment. I think that to do something powerful in terms of quantum hardware, we're also going to need to use lithography. We're going to need to print out very large billions of qubits. Okay, so I'm particularly interested in solid-state devices that exhibit quantum mechanical behavior and systems that we can actually control and study. So this is a picture of the type of quantum system that we're working on in my laboratory here at the University of Sydney. These types of devices are actually semiconductors, and nanotechnology of semiconductors for quantum computing and other applications is really extreme nanoscience. This is a picture of a laboratory of a collaborator. It's a machine called the molecular beam epitaxy machine. It's amazing. What it allows you to do is grow one atomic layer at a time a material of your choice. I would like to grow gallium. Okay, there's an atomic layer. I want another layer of atoms of gallium. And another, wait, hang on, now I would like to put some aluminum in. Okay, good. Put one layer of aluminum. One atomic layer. So we're building up a sandwich. Imagine that. I'd like some ham. I'd like a little bit of cheese, but just one atomic layer. And a stack of whatever you choose. One atomic layer at a time. That's tremendous engineering, tremendous nanotechnology. What do we do with such a thing? Well, here's a cross-section of it. Very, very carefully grown. Look at the dimensions here. Okay, 50 nanometers of gallium arsenide. That's a semiconductor. 800 nanometers of more gallium arsenide. Okay, now 40 nanometers of gallium arsenide doped with aluminum. Slightly different semiconductor. Very slightly different. What happens, very interesting, and this is, it's actually technology that's in your phone. Can you see that green line? That green line is a two-dimensional plane, a sheet of electrons coming out of the screen at you. It's sandwiched between two slightly different semiconductors. It's like a layer of cheese in between two pieces of bread. But we're talking about cheese that is maybe 10 to 20 nanometers thick. That green line are electrons, a sheet of electrons. And what we're going to do is, using the tools of nanofabrication, is come along and then on the top of this thing, put down tiny metal electrodes. Okay? Tiny metal electrodes, which if we attach to a battery and make them negatively charged, they will repel the electrons underneath them. Does that make sense? That thing there with an arrow is meant to be an electron with a spin, a little magnetic moment associated with the electron. And I put negative voltages on these gold electrodes that are sitting on the surface. Those negative voltages, of course, repel, deplete the electrons in the green 2D layer, leaving just a small puddle behind. What's nice about this is I can change in the lab the voltages on those gates and shape that two-dimensional electron gas to be what I want it to be. I'm going to use that as a system to confine and trap single electrons and to manipulate them quantum mechanically. How do you do that? How do you put down tiny little metal electrodes? You go into a clean room, you dress up in a bunny suit, you get really tired because it's loud in there and it's yellow lights. You make use of equipment that costs $3 million, electron beam lithography. It's the foundation of this type of nanoscience. And you use that to pattern to expose a substrate to a beam of electrons such that when you deposit metal, you can see it overlaps like this. If I remove that purple layer by dissolving it, I'm left with just metal in the other region here. Okay, so these are types of techniques that we call broadly lithography, and they're the way in which we pattern these tiny structures to create what we want in a clean room. Here's what devices look like. These are actual devices that have been made by my students and postdocs here at Sydney. Have a look at the length scale. So that scale bar there is 1 micron, 1/1,000,000th of a meter. How big are these metal electrodes? You're looking down on the surface of one of those semiconductor heterostructures, that layered sandwich. You're looking down on the surface. And you can see regions there. They're not real electrons. Those green things are circles that we draw on to indicate where the electrons go. Let me show you what happens as you zoom out away from this structure. You have to figure out how to connect it to the outside world. There are layers of that. We have to fabricate using nanolithography, all of these interconnect layers that scale up and out to something that looks like this, that eventually, on a good night, a PhD student mounts into a printed circuit board package that we've designed as well and constructed. And then eventually, here's the fun bit, attach it to the end of a dilution refrigerator and cool the whole thing down to 10 millikelvin above absolute zero. So why do we want to go so cold? So remember I said we want to decouple from the environment. We want the cat to stay in a state of dead and alive. Okay, so we're trying to decouple the system from its environment. We want to slow down all of the jostling thermal motion of all of the atoms at room temperature until that fragile quantum mechanical behavior is evident that we want to study. We have to do that at very, very low temperatures. Minus 273.14 C. That's what it looks like in our lab. The sample on the end sits in a very high vacuum at those temperatures, and then we interrogate that tiny nanoscale device with all of this other electronics that you see around. We need to make measurements very quickly, so I like to say we're combining nanoseconds with nanometers with millikelvins. It's extreme limits of size, time, and temperature. Okay, in the time I have left, which is not very long, I'm going to actually show you some real data and what it looks like to do measurements on such a system. Let me say, if you're imagining a career in science, this is the type of thing that you would do. I mean, it could be very different to this, but it would be of this type, meaning it's your hands that are controlling the motion and detecting single electrons. It's possible. So I hope that this thing makes sense. You're looking at the metal electrodes on the surface of the sandwich. So you could imagine that at the layer of that electron gas, wherever there's a negative voltage applied to these metal electrodes, underneath it, there are no electrons because the negative voltage repels the negatively charged electrons. In the middle here, we've got a puddle of electrons, and that N means that we've got N electrons. I don't know how many, N. It's a little puddle. And here's something really interesting. Off to the side, we made a tiny little constriction, a neck, just an almost broken neck of the electron gas. If you pass an electrical current through here and measure the resistance of that tiny region, if the number of electrons in the puddle changes, let's say one jumps out, have a look at what happens to the width of the neck. See that? Because electrons are negatively charged, when one leaves that region, it opens up the neck a little bit because all the electrons are charged in the system. If you measure the resistance through there, the resistance depends on the width, and what you end up seeing are little jumps in the resistance corresponding to single electrons jumping out of this puddle, this quantum dot. That's kind of amazing. You can see in the lab little clicks corresponding to single electrons in a solid-state semiconductor device at 10 millikelvin. We want to go further than that. What good is one quantum dot? Why not have two? What's really interesting here is that by controlling the voltages again on these gates, you can dial up whatever playground you want. The numbers tell you the number of electrons on the left, the number of electrons on the right. Okay, so moving along the horizontal here, we're adding 1 electron, 2 electrons to the right-hand dot. Moving vertically, 1, 0, 2, 0 electrons to the left dot. Moving diagonally, we're adding electrons to both dots. What I'm showing you here is that by controlling voltages in a lab at room temperature, you're talking to a tiny device down there and you're dialing up whatever number of electrons you want in each dot. I'd like 3 on that one and 2 on that one. And those of you that know something about chemistry, something about quantum physics, should start to see that in some ways you're creating an artificial molecule. It's like that's an atom and that's an atom, and there's some covalent bonding between them, and I would like, hydrogen with 1 electron and helium with a number of electrons. It's an artificial system where you can actually control the number of electrons, the confinement, the energies, the overlap of the wave function. Our friend Pauli tells us that electrons are highly antisocial. If you take two electrons and you tell them to occupy the same region of space, they look at one another and say, we better have different quantum numbers. Otherwise, I'm not occupying the same region of space as you. What that leads to is electrons stacking up on top of one another in energy. And it's a very interesting system, this one, because if we include the quantum numbers, the spin, angular momentum, then by pushing electrons together, they'll only go together if their spins are anti-aligned. If they're aligned and we push the electrons together, they won't go. And so I want to sort of just give you a flavor by saying that by controlling and manipulating these single electrons and trying to move to different states, here's one where there are two electrons occupying the same quantum dot, 2, 0. Their spins must be anti-aligned. We have a way of now connecting the spin quantum number to the position and to be able to control and manipulate that. That forms our quantum system in which to do quantum computing, quantum information processing. At least, look, it forms the basic building blocks. So here we have what's called coherent oscillations. These are oscillations in the probability of one of these electron states. And the fact that you see oscillations tells you that you have superposition states. So where are we today? We can create these single building block systems, qubits. We can put them in superpositions. We can do measurements. And after some time, find that the spin is up or down, the cat's dead or alive. Then we can put it in another superposition. So we can manipulate single qubits. We've gotten a little bit further. Colleagues of mine at Harvard have coupled now one qubit to another qubit. It's like a NOT gate. It's called a control NOT gate. It's the building blocks of actually scaling up this kind of quantum technology. And what we're trying to do over the next coming years, these again are devices from my lab, is start to develop much more complex circuits. This is not an Intel chip or the quantum version. It's something as simple as a few logic gates strung together to create, an adder or a counter, or this is where we're at. But we're learning the tricks and we're learning what's possible. And our view, our aim, vision is to scale up the number of quantum systems to large enough numbers that we can start to run some of those powerful algorithms that I told you about. So let me wrap up. I hope that I've given you at least some taste of what it means to do experiments on quantum systems. If you go back 100 years or even 50, 60, 70 years, these guys should look pretty familiar to you. Doing thought experiments around the fireplace with a nice single malt in hand saying, imagine an electron coming out of an atom, and imagine you did a measurement on it, and then imagine you did another measurement. They never actually thought that somebody one day in a laboratory would do a measurement on a single electron. We can do those experiments that were the realm of thought experiments in the early years of quantum mechanics. I think that's a tremendously exciting opportunity to actually do those types of experiments and to not just wonder, but to ask nature, how does it work? Last year, it was exactly these types of things that were awarded the Nobel Prize. Okay, so these guys are active members of our community. We see them at conferences all the time. They're both terrific people, and it's a real statement, I think, about where this field is going to award them the Nobel Prize at this point in time for controlling individual quantum systems. At the University of Sydney, as you've already heard, there is a major investment of the federal government, an investment of the university, an investment also of individuals like John Hook, who's sitting here in the front row, to take these ideas and ramp them up. How do we really, really get this stuff going? Okay, you're showing building blocks of quantum systems so you can control and manipulate single electrons. Make the thing. Make something useful. Why don't you make 100 qubits? That would be powerful. 1,000 qubits. How do we do that? Think of the tools you need, the laboratories you need. I told you how fragile quantum systems are. What does that mean for the specifications of a laboratory? You're going to do that in your backyard? You need a laboratory with extreme conditions, very low vibration, extremely quiet electromagnetically, temperature stability, humidity, carefully planned out. I can tell you that the last few years, 3 years actually, we have been weekly spending an enormous amount of time planning such a facility, such a building that includes clean rooms for nanofabrication and precision measurement laboratories for just the type of science that I've told you about. So I want to show you now a little video that is a fly-through of the proposed facility. It's not a pipe dream. The video I'm going to show you was created by Lend-Lease, which I can now tell you is the chosen contractor for the job. The contract is signed, and those guys are starting construction in a month or so. You can see the site behind the physics building right now being prepared. So take a look and get a sense of what it's going to look like. You should be able to identify the existing physics building here, and behind it is this new facility. So this is effectively a $90 million facility, co-investment of the federal government and the university. It has clean rooms, cafes, meeting spaces, precision laboratories. That's the clean room. People in bunny suits. If you're interested in the science that I've been discussing and you see yourself wanting to play with quantum systems, wanting to create and invent your own nanoscale systems, I truly believe that this is going to be the place to do it in this country. The Australian Institute of Nanoscience. There won't be any ghosts. As Harry mentioned, lecture theatre. It's where we hope to hold the next schools. So let me finish there and acknowledge also the members of my team who are the ones actually doing all of the work. Thanks very much. I'll take some questions.